Okay, so today we are going to talk about convolutional neural nets. So before we had two industry talks, I was talking about like basics of neural nets. We talked about what's a neural net, what's backprop. Backpropagation was basically you're trying to nudge your neural net in a direction, and then the direction you want to go will be backpropagated to all your weights in your neural net. That's what backpropagation is. And if you remember, a potential issue that you should always keep in mind is when you're doing backprop, you're computing gradients and you're pushing that error through, right? And those gradients can have two problems. One, vanishing. And the vanishing gradient doesn't mean something too bad normally. Vanishing might also mean you're at the ideal spot. There is no much place to change. But it could also be just because your activation function got saturated. Remember that sigmoid curve? There is no place for sigmoid to move. That's why maybe your gradient is dying. Okay? And that doesn't mean necessarily you're at an ideal spot of your weights. So vanishing gradient is a real problem. You could also exploiting gradient, which means gradient might become too large. You're changing too much at every single step. Right? And this is something you don't want either. And for exploiting gradient, one thing you could do is you can clip. You can say, if it is bigger than the norm of the gradient is bigger than, say, 100, I take the gradient, I divide it by itself. Now it became norm 1. So that's clipping you could do, and we will see more tricks today. So exploiting gradients will also come an issue in this convolutional neural net stuff. That's all I think more or less you need to remember from our previous class for today, but of course, always go back, look at it. And now let's talk about convolutional neural nets. And I want to motivate it from a practical problem. Not so useful though, but can you find Waldo in the picture? So let's say you're going to design a neural net which is going to find Waldo in if it exists in this picture. All right. So what would you like that model you're designing to have as properties? What do I mean by that? Let's say, think about the neural nets we talked about in the previous class. It takes a vector, right? It multiplies it with a matrix, puts a whole bunch of activation functions on it, keeps going. That's how they go. Fine. But here, this whole image is going to become a vector. And now, if I would be doing the neural nets we talked about, multi-layer perceptron, MLP, it would be treating the whole vector with different weights, right? So let me write what I mean. So I need a little bit of space for this. So let's say this whole thing became a vector X, and my neural net is multiplying. And this X will have a big dimension. My neural net will multiply it with a weight matrix N. Let's say X is in Rn. And say weight matrix is D by N. This means this matrix has got D rows, right? And it's multiplying your vector with every single row. It's spitting out a D-dimensional vector. Now, what is your first feature in this vector talking to inside the matrix? If you try to see how the multiplication goes, first feature is always talking to first column in your matrix. It's never talking to the second column, right? And vice versa. So every feature in this type of neural net kind of treated differently, right? So the third column of your matrix has nothing to do with the first column. But then I'm treating the third feature and the first feature differently, which is probably a good thing. I want to be flexible. I want to capture the features, etc. Fine. But when you come to image-related applications, you're trying to spot Waldo. Waldo here and Waldo there should be treated the same. Okay? If that's your goal. So if you take our neural net stuff that we discussed, apply it straight up to images, that will probably give you a problem. And in technical language, so this I took from this book called Dive into Deep Learning, D2P. I'll put a link. This picture and this writing is from there. I think their coverage of this topic is pretty good. I gave a link to this book earlier. I'll put it again today. It's an online free book, pretty good. It has code and everything on it. All right, and our textbook is referring to it all the time anyway. Okay, so all right, so we want translation invariance, which means the thing you're trying to detect showing up in the 100th feature versus second feature shouldn't matter. But if you do standard stuff that we talked about, it will not be that way. Okay, that's the first thing you want. What else? Locality, in the sense that at least in the early layers of your neural net, it should be likely thinking about a feature and a feature locally. Like if you have a pixel from somewhere in the picture, you don't want that to be thinking through all the pixels in the picture. Do they have a relationship with this pixel? You want it to be likely thinking about that pixel and the pixels around it. Do they make some feature that I'm trying to detect? You want it at least early on locally. If you're trying to build a neural net with many layers, maybe later layers will try to figure out that global features that you might need to think about all the pixels together. But at least in the first layer, you want to be local. Okay, what else? So apparently they wrote what I just said. And now we are going to try to talk about the same thing in a mathematical way. Okay, so let's say this was my pixel. And for the moment, let's just think about grayscale. Your pixel is like 0 or 1. It doesn't have like 3 channels like color stuff. And then since I want my neural net to think about it locally, likely, think about your picture like as it is coming, like an image. Don't think about it like a gigantic vector. Instead, think about it literally like a 2D picture, okay? I got a pixel right here. And then since I want to be local, suppose my neural net should look at this and should be considering pixels around it in a local window. That local, you're going to get to define it. How big is that local thing? But at the end, it shouldn't be the entire picture. All right. And what else I want? And I also want it to be translation invariant. That means this pixel being ij, like say 1, 3, or being someone right there, 100, 200, shouldn't matter. I want it to be translation invariant. So basically what I'm trying to do is I'm trying to put patches on my image, local patches. They should do something to capture features I'm looking for. And I want to put a lot of such patches and combine them and get something out of it. Okay. And if I try to do it like mathy way, let's say hidden ij, next layer in your neural net, you can put some number like a bias, that's fine. Plus x, I minus k, j minus l, multiplied with a weight. What do I mean by that? So you're getting hidden ij, and you think about what kind of input stuff here can be related to that output. It could be 2 steps behind here, then you put a weight on it, 2 steps up, you put a weight on it. Everybody in this window will be related to your next output in your second layer, okay? And how do I phrase it mathematically? This is your ij. Go k steps, say left, and l steps down. Here is your pixel. Whatever your patch is putting as a weight, here is that weight. And this is, roughly speaking, what you expect to get out of this. Put that patch locally, multiply all those weights with all the pixel in the patch, and you'll get a number of it. That's kind of what you're kind of going at now, because we want local, we want translation invariant. This is the picture you immediately get if you want those properties. Okay. And if you watch the videos, once again, this will already start looking at you as a convolution, which we'll get to in a couple of minutes. And if you do this, you can spot the Waldo like here. So this weights in the patch are what we learn through training. And if you learn right, then those patches will start detecting what you're looking for. And it should be translation invariant. Here or there, doesn't matter. Okay? Okay. Now, how do I go ahead and do this. So far, so good. Does it making sense? All right, good. So K and L, yeah, I should maybe think about writing this more carefully, but basically, yeah. I see. So I should allow this to be probably negative, left and right. Yeah, basically box around it, and you go like one step left. There's a weight corresponding to there. That's what we are literally doing. Yeah. All right. Now, let's remember what was convolution, and let's try to do it very discrete. Normally, convolution can be defined with any random variable. For example, you're computing convolution of two uniform random variables, right? What is uniform? Between 0 and 4, that's what you're computing. Pick any number uniformly. And between 0 and 4, pick any random uniformly. Take a convolution of these two randoms. Okay. Now we will do something much more simple in a way. My pick is going between I plus L. Basically, I'm looking at a discrete convolution. So think about two. Let's say I have a set here, 1, 2, 3, 10, and I have another set, 1, 3, 5. And you pick a uniform number from the set in the left, you pick a uniform number from the set in the right. These are two probability stuff. Now take their convolution. What you're gonna get? Let's say, what is the probability of getting 11 off of this combination? Well, probability of getting 10 times probability of getting 1. And if you remember the picture of two dices getting convolution to each other, the thing in the middle was getting more and more higher probability. Okay, so this is literally what we are doing here. Weight minus L. So I'm convoluting, taking a convolution minus L up to plus L with this I minus L, I plus L. And I'm looking at kind of what is the probability of getting I. Minus L plus L, blah, blah, blah. You see they all sum up to I, right? Okay. And now, since we want to do computer science, we should tweak the math, right? So we don't do convolution as it is in math. We kind of flip the order. When people say convolutional neural nets, they don't mean the convolution that people have been using for hundreds of years, okay? They mean this one. So instead of summing up to I, they just flip the order. So I minus L was going with L, okay? Now they're gonna go make I minus L go with minus L. All right, so it's like you take these weights and flip their order essentially, okay? When they mean convolution in machine learning and computer science, this is usually what they mean. And the proper word for it is actually cross correlation. Now you're looking like a dot product if they correlate or not, essentially. But usually the weights are symmetric, so they end up being the same thing anyway. That's why people use convolution for this. Yes. So I think it's convolution. So then you get cross correlation. So yeah, so you don't mirror, you just convolute in standard convolution. So here it's mirrored, as you see. It was summing up to I. Now it's mirrored, so it's not summing up to I, but minus L's match. So what you have in mind is literally this. So you have a good intuition for what we are going to do today. Okay? Literally, you take the standard convolution, but you do this mirroring or flipping. That's what cross correlation is. If people are careful with their wording, they'll use this. If not, they'll just call it convolution. Okay? Not so important, just making you aware of what's going on. And here is a illustration from a convolution. So we're taking convolution of the stuff on the left, and the weights that we use in the convolution, this W stuff, they have many names. It's like some poets love in love writing a poem, like 100 names for the same thing. So it's like kernel, filter, weight, convolution, patch. They all mean the same thing. So it's just like you take this thing on the right and you take this cross correlation with the stuff on the left. So I think this, yeah. So you take 0, 1, 2 times 1, 2, put it here. Okay. So literally that's what you do. You put this 1 times 1, 2 times 2, 5, put it here. That's what you're doing. You're like sliding it through. Now I see what you mean. Maybe what you had in mind was the correlation definition. Okay. I see what you mean now. Okay. Now I understood it better. Okay, very well. Anyway, so is this illustration Making sense if you look at it here? I'm taking this, multiplying with the stuff, putting that number right there, and sliding the window. Okay, that's what I'm doing. Anyway, I'm confused. Let me not confuse you. Think about it. Okay, all right. Yeah, so you take this here, 0 times 1, 2 times 1, 2. Go to the second, 1 times 1, 2 times 2, 4, 5 second. You just slide it over. Okay. Huh? We are gonna get there. It's just basic convolution yet. Okay. No pulling. We are just defining convolution. We'll build it from scratch. Okay. Very good. Okay. Now this was 1D. How would it look if I to 2D convolution? Same story. Take this guy, multiply, put it on the right, start moving it around, and get your output. Okay. And one thing you realize is my input was 3 by 3. Because of the shape of my kernel or filter or convolution, the output did not come out as 3 by 3. It came out as 2 by 2. Why? You first put this 2 by 2 square here. 1, 2, 3, 4. And that's what you get. Okay. So you lost some of the input you put in terms of the size of it. That's what I mean. So the output is smaller than the input. Okay. And this is kind of normal because when you're doing convolution, you're kind of zooming out locally. You're losing some resolution because you don't want to capture every single thing in that local neighborhood. You just want to capture, is there a Waldo or not, whatever you're looking for. So you can zoom out. You have some leeway, hopefully. Okay. And if you still want to keep the output the same size, we will see some trick very soon. You can do that. Okay. So this is how a 2D convolution looks like. And here is the MATI version. So this is from our textbook. And our textbook takes the stuff from this reference, which is that diving into deep learning book that I was referring to. Yeah. All right. So if you write down this picture you're seeing in MATI way, this is how it looks like. This is your weights. This is your input. And you're making this guy go through your input and you're getting an output to write. Okay, very good. Now, if I would like to keep the size of my input, I don't want to get like 3 by 3 in, 2 by 2 out. I want to put like 3 by 3 in, 3 by 3 out. What could I do? I could do something called zero padding, okay? What does it mean? So let me show you this, then I'll show the picture. So if I put A times B stuff, if this was my image, height times weight, 3 by 3 in the example before, usually, 258 times 258 something. And if I'm using a patch A times B, the output becomes like you try to put the patch on the left and you slide it over. But when you're at the very end of your patch is touching, but the beginning is not at the very end. It is right here. Okay. So this is the size of the output that's going to show up. You don't have to see this minus A plus 1, whatever that matter is on top of your head now. If you're not seeing, if you're seeing, that's cool. What you need to see is like when I'm sliding that patch through, it's not able to go till the very end. So I'm going to get an output smaller for sure. Okay. And if you want the same size of output, same in, same out, the trick is simple. Add a whole bunch of zeros. The number as much as that you're losing. So this was your input size, add this many zeros and this many zeros. Then when you slide, those zeros will give you a place to keep sliding till the end, essentially. That's called zero padding. If you do this trick, you get the same size out. Okay. And the picture way of looking at this is right here. Zeros outside. And yeah, you see. So because of zeros, the guy was able to put the patch till the edges. Right? So far, so good. That's called zero padding. And we will have one more trick. Oh boy. Okay. So this is called strided convolution. And this is the second trick in the toolbox after zero padding. What is it? suppose I'm doing this patch. I'm moving here, 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 going around, right? So the first patch and the second patch, they are both 3 by 3, but they have a huge overlap. So I'm just sliding it one. They're overlapping on like 6 entries here. So you would expect the output from these two patches to be very similar. So it's like kind of wasting your compute. So what you do, you say, okay, I want to ignore very overlapping patches. So you decide up to how many you're skipping. So it here says SV2. That means every 2 of the patches will be getting it. I'll take one, I'll ignore the other one. I'll take one, I'll ignore the other. And it says SH2. That means I'm doing the same when I'm going up. You know, only half of the patches gets in because close neighbors are giving me similar numbers anyway. That's called stride. Okay. So reducing, like if you're doing 2, you're reducing half both ways. You could do 3, 5, whatever you like. You decide up to what many patches gets to the next level. So good? Yeah. Strided convolution. That's the technical word they use. Yeah. Yeah, the thing we are doing is called convolution, and this thing is called strided convolution. Okay. All right. So, and you could update the math that we were seeing there. You could also compute if you do this SH, SV, and then, zero padding, whatnot, how many things you will get out right here. That's so important. Basically, you're adding the zeros, and then if you're doing this much striding, you're dividing by that much. It's pretty intuitive. Okay. All right. So far, so good. Now, how about when I'm dealing with actually color images? At every pixel, I will have 3 channels, not only, grayscale. Then you could do patching on every channel as you wish. Okay, and I could also write this in a mathy way. You'll see like a tensor instead of a matrix, right? So you'll start thinking about like a Rubik's Cube place, okay? So you can write the exact same thing in just a little more looking bigger like a monster, but it's the same idea. Okay, so that's not a problem. You could do patching on every channel separately if you like. For example, here what they're doing, they got 3 channels in, and they decide to spit out only 2 for some reason. So this is their patches. They take 2 patches, 1, 1, 1. It goes here, and the other one goes here. And since I have 2, I got 2 out. That's about it. Okay. So you could play all these tricks in your design. You could change the channel size. You could even flatten the whole image into just one vector. All this is allowed, right? And we'll get to those kind of stuff very soon. Okay, so far so good. So this is the convolution part. And one interesting convolution is though, like if I just take one thing on its own, suppose I push the convolution to some extreme, I'm just taking the stuff on its own. Then it's going to be literally like taking a weight for every single one and spitting out. So if my convolution is 1 by 1, it's an extreme case. It will start looking like what we were doing before in the previous lecture. It's going to be starting looking like literally I'm multiplying with weights, spitting out. Okay, that's sometimes useful. So keep that in mind. There's a lot of flexibility on designing your patches, as you see. And next thing in convolutional neural net toolbox is pooling. What is pooling? Well, there are different versions of pooling. For example, here you see max pooling. I take a 2 by 2 window, and I take the maximum guy in that window. For example, here it's 4. And I do it again. In the second window, it's 5. Here's 7, it's 8. Okay? So this is one pooling. So basically, you'll have a window as your pool, and you will decide on your action on it. I'm taking max here. One thing you could do is like you could take average. That's called average pooling. Okay? And you could sometimes do what's called global average pooling. And I did not want to write this with my handwriting, which will be sore on your eyes. So I just clipped it from the textbook. So if you're pooling the whole thing, it's called global average pooling. That means like I got so this is my feature stuff, height, width, maybe 3 channels. And I'm just making it go out like 1D. Right? So that's one thing you could do. You're globally averaging everything, whatever that means. Okay, so far this is our small tools. What's next? Now let's try to see everything we talked about together so far. This is your input image. And you put a whole bunch of convolutional layers. You could also put activation functions, our usual trick, let's say RLU. And after you do these layers, 1, 2, 3, whatever many layers you like, you do some pooling operation, max, average, up to your taste, okay? Then you again do convolution layers. This is the classic design. We will see a lot of different architectures today. This is how it was classically, okay? And then you again do like pooling, again convolution. Eventually, at the very end of the story, you're gonna go flatten your image thing and make it like a vector. And then after that, it's standard multi-layer perceptron type stuff. After you make it into a vector, you do what we were talking about in the last lecture. And you output depending on your goal. If you're trying to classify digits, your output should be 10 classes, and then you're trying to estimate the probability of your image belonging to one of those classes. Depending on your application, that determines the last output. Okay? Yes, right. They are usually usual activation functions that, yeah, exactly. So they are the stuff we have already seen. Very good question. Yeah. But what you said doesn't sound like a bad idea. I never tried it. But... So basically what's going on is like, maybe this is, yeah, maybe let's look at it this way. You take a window, you do all that convolution. At the end, you get a number out of it. Then you put that number inside an activation function. If that number was high enough, neuron will fire. Okay, you're putting activation functions on top of convolutional patches, basically. Yeah. Okay, this is how it used to look like when it started out. I forgot the name of this thing. I think it's by a Japanese scientist, maybe even in the 70s. And at the time, they were literally trying to emulate how they think our visual cortex is operating in our brain. So what was it called? Neurocognition science or something. So they were trying to mimic. That was their idea. Okay. All right. Now let me show you. Sorry. I think that's like an engineering motto, right? So if it is not broken, okay. Let me show you what got Jan LeCun on the map back in the day. So he now leads the AI branch of Facebook or Meta. Also a professor in, I forget, NYU or Columbia. This is what he got when he's, I think, maybe 60 now. So since 80s, though, this guy has been consistently working on machine learning, even though it wasn't cool back then. So one of the first things that got Jan LeCun on the map as a scientist was called LeNet after him. And it's, or Lina, I don't know. Or maybe French accent, he's French, LeNet. And it's called LeNF5 because it's got 5 layers into it. And I'll get into this a little bit more, but let's look at it cursorily first. This is your image, 28 times 28. And then I got some convolutional layers on them. Then I got some pooling layer. Then I got a whole bunch of other convolutional layers. Then I do some pooling again. Then after that, I flatten. I do dense standard multi-layer perceptron. I get out 10 options because this was trying to classify images. Okay, let's look at this in a more simple way. Then I'll get back to what I was showing you. Okay, so image gets in 28 times 28. And then I got 6 patches. They're all 5 times 5. Okay. So I got 6 times 28 times 28 output. So every patch gives me 1 output, and then I have 6 of them. And that happens for every single entry. Okay. Then I want to go for next one. I'm going to do 2 by 2 averaging. But I don't want to lose the edge cases. So I put some zeros, zero padding. And I go over all this stuff and I keep averaging over and I put them out. That's what's going on in the next one. Since I'm averaging over 2 by 2 into 1, you're going to get half. So 6, 14, 14. I was trying to keep track of the numbers when I was writing the notes. Okay. Yes, so here there's a padding. Here there's going to be a strike going to the next level. It's not a padding, it's a strike. That's why I lost half the thing. So very good question. Exactly. So I'm striding by 2, and in the entry I'm padding. So first you pad, not to be able to go till the edges. Then when you're outputting, you stride. So when you're striding by 2, that reduces the dimension to half. And since you zeroed, you don't lose more. If you wouldn't do zero padding, you will also lose from this 28. It will be like 26, 27. So you want to just half it. So you put the zeros to make it work, and you're halving, so you get 14 by 14 out. Okay, then it goes to the next level. Then this is averaging pool. Then in the next level, again, convolutions. This time, there is no padding. So I was computing what's going to happen on the right. And that comes out as 10. So you go from 14 by 14 to 10 by 10, 16 outputs. Then again, another averaging layer. Since we are striding, we are also like halving. And then after that, you flatten. You don't see images anymore. You just see vectors. You put them into your dense multi-layer perceptron. And at the very end, I forgot to look up his objective function, but probably it's cross entropy. He's trying to classify and make the probabilities lined up. So that's a more simple way of the same thing. Let's look back at the picture. So 28 by 28, 6 convolutional layers, 6 times 28, 28. There was some zero padding to make this work. And then again, 6 pooling layers, but we are also striding, so we got this 14 by 14. And then yet another 16 convolutional layers. There is no zero padding, so I got this 14 to become 10. And after this, we again do some pooling with striding, so we halve. And after this, he decides to flatten, go into dense layers. First, whatever dimension of this flattened thing is, that goes to 120 out. Then from 120, you go to 84. This is literally a 84 times 120 matrix. Okay? And you go till 10 and you train. And after a few epochs, it was so good, turns out, that it was not distinguishable from just noise in the data. So like maybe 3 epochs gets you almost to the noise level. But then they realize they don't only want to classify the digits in the writing, they want to see it inside a more bigger writing. Let's say I'm writing a letter to someone. I wrote 5, okay, but it's inside a bigger picture in a way. So you first want to do some segmentation, then classification, okay? They also do some very clever algorithm for that. I forgot the name. It was a probabilistic way to segmentation. And then after that, they put this on top. Then it runs very well. And I think then USPS decides to use this. It's deployed back in the day in USPS. So this is one of the first success stories of convolutional neural nets. Next one in the line is AlexNet. So maybe you heard of this guy called Georg Hinton. Sometimes people call it, what is it? Godfather of AI or something. Lots of fancy names. And then what was the other one? Ilya Sutskever, maybe? I don't know how to read his last name. He used to be in OpenAI, and then this, I think he now started a different company for safe AI. Very famous, right? But the guy who did all this breakthrough was someone else working with these 2 famous guys called Alex Krzyzewski. So the neural net in 2012, who won the image competition, was named after this guy. They were 3 people, these 2 other famous guys and this one. So this one turns out to like to keep himself quiet and doesn't talk anywhere. But everybody says he was the engineering genius behind this story. So, I'm not an engineer, so I cannot comment much on it, but seems like there's an agreement. What they managed was an engineering tour de force, right? So here is their neural net. First of all, let me tell you their goal. So you will go after this ImageNet dataset, and you're going to classify, and unlike digit, which have 10 options, you got 1,000 options in the output. And the accuracy is the metric, basically. So you develop a model, you run, you check how accurate is it, then you compete with the other people. That's this competition. All right. So, and every year, people go like incrementally a little better, a very tough competition. Apparently, they improved by far in this 2012 competition. That's what got these people famous. And let me show you the neural net they designed. So this ImageNet dataset is like cropping the data a little bit. So you don't get 258, you get 224, 224, and 3 channels, right? That's the image input. That's where you start off with. And then they got a convolutional layer with striding, then max pool layer, another convolution, another stride. And here they do something interesting that was not done so much before. They put convolutional layers on top without any pooling. Okay. Before, people were used to like convolution pool, alternating. Here they put them on top of each other. And then there's another max pool, and then you put dense. And if you compute all these numbers, it's kind of a sizable neural net. Okay, not as big as the ones today. So they somehow intuitively understand if we scale this up, it's going to perform better. And they have 2 GPUs, turns out, and they push it to the limit. That's basically the story. They do all the tricks they can to get the most computing out of the 2 GPUs they had, a whole bunch of tricks. And they push it to the limit of their scaling with the compute they had, and this is what they get. And it performs pretty well, yeah. So kernel, you're learning. That's literally what you're learning in convolutional neural nets. So kernel, you decide the shape. So here you're using 11 times 11 patches. But what is inside those patches is literally what you learn. So that's why I was saying, if you compute all these numbers, you're actually learning a lot of parameters. Okay. So you got like million stuff here. I did not compute total number. You're learning nine parameters there. Exactly. Very good. Any other questions? This is AlexNet 2012. Yes. I mean, probably if you work on this a lot, you'll have some intuition, but those stuff is not written. And if gurus know it, and I did not work too much on image processing. So I'll not be able to give you very deep insight on this. But kind of how big are the patches defines how much resolution you want to put on. That would be one thing. Like, what are you really after? How much zoom out is possible? But other than that, we will get to something called inception soon. Since they didn't know what to pick, they created a design which combines a couple of patches, and the neural net decides to put weight on which. So that's coming a few minutes now. So that was one other breakthrough. Very good question. So, and now there are some tools trying to search for good architecture through experimentation for you. And I'm fairly certain if it is not already out, should be out soon, that they will make an agent version of it, probably. You'll just give the agent and then let it watch it to do that for you. But how good that would be, I don't know. But I would expect eventually you'll get there. Whatever we can figure out experimentally, we will let an AI agent figure out for us. Well, that would be what I expect. Okay, so that's all I could give. Not a very great answer, but more or less. Yes. Yeah, exactly. So how much downsampling you're going to do depends on how much resolution you want to lose. But Ben was asking, like, how do I know what kind of patch to put where? So, yeah, exactly. All right, so this is like (2012) breakthrough. And 2015, we are going to talk about it too. And that seems to be going below human average error rate. All right. Okay, next in line is related to Ben's question. So what kind of patching I should put where, right? Since there seems to be no like very principled way to think about this, people in Google design this module and they keep stacking up this type of stuff on top of each other. And the idea is I put several different patches inside a module. And when the backpropag is backpropagating, from the data, it should learn how much weight should be going to what. Trying to pick the correct patch size for you somehow. And they were doing this pun after LeCun, they called it Google LeNet or something. They were having fun with their naming. And later people called it Inception, okay? And this was the next kind of breakthrough about 2015, but that's not the one won the competition. That's gonna come next. And in Inception, the main idea is this Inception module. You put a whole bunch of different patches next to each other. And they also put a max pool layer here, turns out. And you let the backprop decide for you which patch was the good one. Okay, now let me show you a little more about this architecture. So this is a simplified version of this Inception. So these are Inception modules. First, they start off with fairly standard, convolution, pooling, etc. Then they keep stacking up these Inception modules on top of each other. And eventually you put into these dense layers, standard neural net, and that's what you train. And they got pretty good results with this. And after that, they got tiny bit unlucky, which I will explain. So same year, a couple of good ideas came along. So first idea, I think that should be, let me check which one I put next in my notes. Yes. So first idea was about stability issues. So when people started going deeper, you started having this exploding, vanishing gradient type issues. When Jan LeCun was doing his small, like 5-layer thing back in the day, you don't have so much numerical problem. It's a small, shallow neural net. But here you keep stacking, and then you lose control of your gradients essentially. And they were having all kinds of issues with that and finding clever ways to remedy. Then two guys came along. By the way, I'm gonna put papers related to this on Canvas. I think I already put it though. So today is like this architectures I'm talking about. If you're interested, I also put the papers that created this stuff on Canvas. If you want to see any technical detail, you can look for it. Okay. So the next thing that came along is called batch normalization. What is it? You pick your batch of data. So you take an image data, it's one input. Of course, you don't just work on one image. You got a whole bunch of image data. Then you take them into batches, right? And then when you have this gradients like exploding, the trick, I forgot the name, but the paper's on Canvas. Two scientists came up with is, let me take my batch. This capital B is the batch. Let's say I got 1,000 images in this batch. However, the batch size is up to you to decide. And then you first compute the average of that batch. Literally, this is every single one is an image data now. And I'm computing an average image. Okay. After that, what I do, I take that average from every single one of my data. I square, I divide by batch size. This, hopefully you remember, is variance from our probability discussions. And then what I do, I normalize my data by subtracting the mean dividing by standard deviation. And they put a little epsilon here because if the variance gets too small, you're dividing by a very small number, you're going to get trouble. So you just give it some juice, so that you don't run into so much trouble. And square root of variance is standard deviation. Now you normalized your data. And now you allow your neural net to learn these two parameters to go for next level, okay? And then they learn these two parameters dynamically. And also you keep putting this batch normalization all over your neural net. So at the very beginning, this is literally standardizing your data. A lot of libraries does it automatically, even without asking you. But what is clever here is they put this trick inside your neural net. So I'm in somewhere in a hidden layer. I got a whole bunch of outputs from my neurons. Then I do batch normalization on them. Okay? So I'm dynamically computing weights and standard deviations and normalizing all the time. Because I don't want to have an exporting gradient after that neuron's fired. I want to normalize once again. Okay? So they put this batch normalization all over inception and make it better. Like very, very close to this paper release, they do this trick, and like a few months later, they make it better. Okay? And now, after batch normalization came along, people try this all over the place, and they realize for some applications, batch sizes are very small. So this starts giving you issues. When your batch size is very small, this stuff becomes very sensitive. Then what do? Then, creative people, they come up with a whole bunch of different ways of averaging over. So batch normalization corresponds to this picture. This capital N is the number of stuff I have in my batch. Batch width height in your image. This is why you get this 3D thing, okay? So your image is, say, 20 by 28 by 28. And then this is one block here, and you got like 1,000 of them, okay? This is your capital N. And your batch normalization is averaging over all your batch. And if your batch is big, that's good. But suppose your batch is rather small. You got like 28 by 28 times 3. It's going to look like very chunky. So what do you do then? Then you pick one of your data, literally. And if you like, you average over the whole thing. It's like a global average. So you can design different kinds of averaging all over the place. And this is the batch normalization, very commonly used. This thing I just said is called layer normalization. You're fixing one of your sample, averaging over. And then, of course, in image data, you also have channels. You can get more creative. If you like, you can average over channels, whatever. The goal here is to normalize the data so that you don't get this exploiting gradients issue. So this batch normalization seems to help a lot. Why it does help a lot is still kind of a mystery. So there is some statistical interpretation of this. There is a paper which claims batch normalization is equivalent to some kind of approximate Bayesian inference. There is another paper that claims batch normalization is like regularizing. We are going to talk about regularization after spring break. It's a trick to avoid overfitting. There are a couple of papers. They all kind of sound to me like economists, though. Economists come and explain to you stuff after that happened. And then they never tell you what's going to happen next year. And that's why I have economist friends. We might work on some projects, don't get me wrong. But that's kind of, for me, not so happy. As a mathematician, computer scientist, engineer, what you want to do is you want to be able to reproduce and guess what's going to happen, right? You don't want to be always the guy who explains stuff after it happens. So the papers about this trick is kind of like that. So it's still a mystery. It's also a question mark if we actually need this or not. Because this doesn't really help too much with vanishing gradient issue. It helps with exploding gradient issue. So another group came along and then they say, well, I can do clipping for exploding gradient issue. So they create very clever dynamic clipping techniques. I'll put the reference somewhere on Canvas. And it's called normalization-free convolutional neural nets. If you Google, probably this paper will pop up. It seems doing pretty well too. So this is still not scientifically very well understood, and I think it's a very important problem. And this type of stuff shows up all over the place. before neural nets, there were similar tricks, turns out, in computer vision. In computer vision, there are classical algorithms. Did anyone take a computer vision class, or anybody is working on that kind of stuff? Like you, fantastic. Did you see like the 7-point algorithm, 8-point algorithm, 3D reconstruction stuff from old days? Now deep learning took over all of them. Maybe that's why you don't see them. In computer vision, it was a kind of distinct discipline on its own. It has its own techniques, and classically, it was very geometric. So it was using a lot of geometric ideas because you're dealing with geometric stuff. And there were issues with the stability, not with gradients, but whatever algorithms you're running. By the way, there's a very good open source package called OpenCV. And all these algorithms, I say you can look them up. And even there are some tricks that seems to work since like 20 years or maybe 30 years, and it still is not explained. Okay. So when I see OpenCV code in this 8-point algorithm, I was like, come on. So there are very standard facts in numeric analysis that they ignored. They got away with it by very clever tuning in engineering. Okay. And I only learned about this because some people from Google found me a couple of years ago. They have these algorithms working, the classical ones, but they don't understand when it is very unstable. Some image data makes it spit out very garbagey stuff. And they want to understand why. We are still not done with it. Hopefully we'll have we had a paper, another one will come out maybe 2 months, but I wouldn't claim we understood it either. Okay. So all this landscape of this kind of tricks for normalizing and creating stability is an important open direction for the moment. Okay. Let's get back to our discussion. After they created this batch normalization and different versions of it, and some people questioned and came up with dynamic clipping, whatnot. This dynamic clipping came much later. But the same year of this inception, maybe less than a year later, another group in Microsoft came up with something called ResNet. Okay, I'll zoom into the picture, don't worry. But the main idea in ResNet is so stupid, you won't believe it works so well. Okay, so the main idea is this. Let's say my neural net was taking some layer. The next layer will be, say, some function on that and some layer. Okay, put that function still, but add what you are putting input as insight. That's the residue idea. Okay, so what? Okay. So this is apparently what an intern came up with. Then the research scientist realized, so when I put this in, when I start back propagating, the back propagation from here goes directly. Because like I'm putting a copy of the thing itself, it back propagates from here back to thing itself. So it keeps a channel all the way through. So your back propagation kind of is always alive. Okay. And of course, then people came up with more different versions of this after this happened. So same year of this inception, this clever intern in Microsoft does the stupid trick, which works super well. Okay. And then they also knew this normalization tricks. Like few months after that inception, this batch normalization paper comes along. So they put them all together. And they create this thing called ResNet. And that's what you are seeing in the graph. So ResNet is this one right here, below human threshold, 2015. They won the competition in 2015, this Microsoft people. And turns out before in 2012, there was this big breakthrough by AlexNet. People in Microsoft were already training neural nets on GPUs, turns out. So they had that insight already. So the honor of first GPU training goes to Microsoft before this AlexNet. All right. So they put all this, previous insight and the new tricks together. And they come up with this ResNet. Let's look at the architecture a little bit. All right, let me see. So the blocks inside will be the residual blocks. We'll zoom into those. Okay. Let's see. So basically, the residual thing is like, let's say, here's your residual block. And since you're putting a copy of your thing inside, fx plus x, the error from here goes literally propagates back right away. And it also propagates through the residual block. So somehow this helps keeping that backprop very efficient. Okay. And later somebody says, okay, instead of adding, this is a plus, right? So you take your stuff, you plus, and you put your residual net, this is the output, and it back propagates. Somebody says, instead of a plus, let me literally concatenate the thing from residual block next to literally whatever I was inputting in, like a vector. Okay. That's called dense net. It apparently works better than this, but it is very heavy to train because you keep concatenating, you get like huge stuff. Okay. So that is, even though it's very accurate and successful, I think this is still better in the sense that you can train this easier. Of course, with the resources these companies have. Now let's look at the residual block. All right. For exploding gradient problems. Or maybe vanishing. Let me get back. Thank you. Let me think about this. Probably vanishing. You're right. Yeah, exactly. So batch norm does the exploding. And this, since it propagates back here, hopefully it keeps your gradients alive. Very good question. Yes. It keeps running through. Yeah. So exactly. So this is your residual block. And this is a copy of your thing getting added. And you put an activation function on top. Okay. And then that activation function kind of back propagates whatever you're trying to do. And it will back propagate to this block and also your extract. It's kind of like going almost cyclic in a way. And we will see more cyclic stuff after break when we talk about recurrent neural nets. They look even weirder, but they work, right? So, all right. So here, what do we see? We see the batch normalization put all over the place. We see the convolution, we see the activation function, and we see the residual thingy, right? And that's your ResNet below human threshold. All right, let me see. Yeah, go ahead. No, so you put your batch together inside your neural net. So that's why it's called a batch. So you don't put just one single data, you put them together. Yeah, you put them all together. Yeah, that's why it's called a batch of data. Very good question. No, I think it was always there. So you have a whole bunch of data. You're going to train your neural net. What you're going to do? Keep in batches. Sometimes you do mini batching, like small number of data in your batches. Sometimes big batching. It's up to you. And then when we get into regularization and learning rates a little bit more after the break, we will touch upon, you have to look at the trade-offs. So this we can already do now, actually, since you asked the question. So let's say I'm doing my stochastic gradient descent. And I'll put all my batch of data together. Okay. Suppose that's my X right here. And I'm doing something like this, right? And I have like a learning rate alpha right here. Yeah. So this gradient now is being computed. The derivative is being taken with respect to all the data in the batch. So the number of coordinates there is defined by the size of your batch, right? But this is propagating through all your neural net. Okay. Now, if you put this alpha big, the learning rate, that means you're being kind of courageous. You're taking a big step in the direction you think is a good direction. If you put the alpha small, that means you're being more careful and a little more conservative in your training. So when you have like a very small batch, it's hard to be confident that the gradient you computed is actually a very good one. Okay. So then what you do, you keep your learning rate smaller so things don't go crazy. But if you have a very big batch, likely the gradient came out as a reasonable one. So you can let your learning rate be a little bigger. Okay. So all this details comes into design considerations. And we will not only do the full batch insight, we will also talk about, like everyone does, stochastic gradient descent, which means you literally sample stochastically the data you're putting in. Then you need to be even more careful with this alpha. How big is your sample size should be taken in consideration when you determine your learning rate. Okay, and there are more tricks to make this learning rates more reasonable. Jan LeCun has a paper that I like very much called No More Pesky Learning Rates. So people were playing with this, like a lot of tricks. There isn't so much like principled way of looking at learning rates. And apparently he got pissed off and works hard and comes up with a couple of tricks to make it in a principled way. But funny enough, I think nothing in that paper got really implemented so much. Let me say just a few things about this, since we are going to talk after break. So this is standard gradient descent, what you're seeing on the board. You will sample data, it's going to be called stochastic gradient descent. Then what would be the golden standard? Okay, if I have the whole compute in the world, what would I do for optimization? You would do Newton's method, okay? You will not do this in practice, but that's going to be the golden standard. Let me show you what that is. Let's say the second derivative, this is your Hessian matrix. Now remember your Taylor expansion we talked about. Let's say A plus X. I'm sorry, X plus H. Fx H times the gradient H transpose, and then plus some error in the order of H cubed. This is Taylor. And the gradient descent you're seeing here only considers this chunk. Okay? It only looks at your function and the gradient and tries to find a good direction to perturb and get it better. It doesn't look at anything related to the second derivatives, and no one looks at the third derivatives. Okay? So now if I want to do better, since at the end of the day, I'm trying to make the point I am better in terms of my objective function. That's all I'm doing. If I take this also into account, maybe I will find a better direction than just taking the gradient. And that's Newton's method. Newton will look like this. You take the Hessian, and not only that Hessian matrix, you got to take its inverse and multiply it with the gradient. Okay. This is Newton's method. You could also put a learning rate here too, if you like. Newton didn't put it when he invented so many years ago, as far as I remember. So this would be the golden standard to do. It will be much better than just gradient descent. But you have to compute this thing right there. And that's very expensive. So what you want to do then, let's say gradient descent is first order. Newton is second order. You create 1.5 order, okay? So what do you do is this, and that's the stuff you're going to see after the break. Let's say this is first order, second order, better. And here is 1.5. X minus some matrix Bx times the gradient. And this matrix should be relatively cheap to compute. And depending on how you create that matrix, your algorithm has a different name. So one of them is called eta grad. The other one is called eta delta. The other one is called RMS prop. So unlucky for Jan LeCun, when he was writing this No More Pesky Learning Rates, Hinton was lecturing, and on the lecture, he invents this algorithm. And that gets much more popular than Lecon's paper. So there is no paper about this algorithm. It's invented inside the lecture. Everybody refers to lecture notes. And then if you go to PyTorch, you will see RMS prep implemented, Ada Delta, Ada Grad, they're all implemented. But the Lecon stuff is not so much implemented. But it's scientifically better, but just a little more expensive. So these are all tricks that I'll tell you what they are to come up with a decent matrix to fix the direction, make it better. But that matrix shouldn't be so hard to compute. And of course, we will compute this by looking at the trajectory we went so far instead of computing the H's. We'll get there. And all this stuff gets into consideration of like what should be your batch size, what should be your learning rate. You can decide your learning rate more principled. Ada Delta, for example, does a decent job. Or you can be courageous. Or you can, kind of switch if you're very careful along the way. If you're confident you're almost there to optimize, you can plug in your Newton if you like. But usually we don't do that. In your training, you can switch between optimizers if you like to. We don't do that so much, but it's easily possible. Because I don't know which one you're using, your PyTorch, TensorFlow, JAX, whatever you're using, you pick the optimizer yourself. And these options are all there. And you can pick it depending on your batch size and everything, okay? So this was a digression, but I did it on purpose because we are gonna talk all about this stuff after break, okay? And I also had time to talk about it. Of course, that was another reason. I hope this gives a short answer to your question. It's not an easy question, okay? It's gonna be there all the time. What should be my batch size? How should I arrange my learning rate? Which optimizer I should use? I'll tell you what you know, but when you go out solving a problem, you'll take that knowledge in practice and a lot of experimentation, figure it out, right? Very good. So that's all I want to say today. I count myself as successful, even though I finished lecture 5 minutes early. I survived a very terrible migraine today. I still lectured. So I think it's a success even though my material finished 5 minutes early. So any questions about convolutional neural nets? So batch is literally how much of your data you're putting inside your neural net at a one pass.
So, 7.
Mm-hmm. So okay. I see the question. Let's talk about this later. Very good question. Okay. So you want more precise technical detail. Okay, got it. Any other question? Yeah, hang on to that. Exactly. So next lecture, not sure. Next lecture will be about recurrent neural nets. So all these LLMs you see, they are recurrent neural nets. And humanity came a long way designing that stuff. Basically, the main problem is designing a machine with some memory. That's the issue in recurrent neural nets. How are you going to have some memory inside your learning system? That's going to be next lecture. I'm sorry. Thank you. Take care. Take care.